So what I'd like to go over is the one of the exercises out of the textbook. So I want to go over exercise 7.3.7. So for this exercise, what we want to do is we want to have the um, harmonic oscillator. We want to solve it in terms of the momentum space instead of the position basis. So we're going to start with our standard Schrodinger equation with the kinetic energy times the wave function plus the potential energy for the harmonic oscillator um, times the wave function is equal to the total energy times the wave function. Now in momentum space, if you remember, the operator momentum is just the momentum. And the operator for the position is I h bar, the derivative with respect to momentum. So if we plug that into the Schrodinger equation, we get momentum squared divided by 2m times the wave function plus 1/2 the mass, the frequency squared, times the position operator squared times the wave function is equal to the total energy times the wave function. So now if we square that position operator, we get momentum, or the kinetic energy times the wave function minus 1/2 the mass, the frequency squared, times h bar squared, second derivative of the wave function, is equal to the total energy times the wave function. So now we've got the second order differential equation, and let's just rearrange it and see if we can get a form which is familiar from when we solved this Schrodinger's equation in position. So if I move things around, minus 1/2 m omega squared h bar squared, second derivative of the wave function with respect to momentum, let's see, plus p squared over 2m times the wave function minus the total energy times the wave function is equal to 0. So let me now divide out the term in front of the derivatives, so that minus 1/2 m omega squared h bar squared. So now we get a nice clean second order derivative plus 2 times the total energy over h bar squared omega squared m minus p squared over m squared h bar squared omega squared times the wave function. So we'll put all that together is equal to 0. Okay, so now let's make a substitution and try and clean things up. So if I go with the variable y, which is now equal to the momentum, like we did in the case of the x basis, but the term I'm going to use here for the b constant is the square root of h bar m omega. Now, what we learned from the previous case when we did this exercise with the position basis is that this y was a dimensionless length. So let's see if y is also now a dimensionless momentum. So if we check the units of the square root of h bar m omega, then what we get is joules times second for h bar, kilograms for the mass, and 1/seconds for the frequency. And then we take the square root of that. So the let's see, the seconds cancel, and I get the square root of joules kilograms, and that becomes a joule is a kilogram meter squared per second squared times another kilogram. So that's basically kilograms meters per second, which is the units of momentum. So this will be a dimensionless momentum variable. So if we put this into our equation, we get the second order derivative of the wave function. Oh, sorry. Let's go back. Yeah. So we say the momentum is the square root h bar m omega times y. dp is the square root of h bar m omega times dy, which means that the second order derivative with respect to momentum is 1 over h bar m omega, the second derivative with respect to y, like that. Okay, so now let's put that into the Schrodinger's equation. I get 1 over h bar m omega, second derivative of the wave function, plus, I said it was 2 times the energy over h bar squared omega squared m, minus h bar m omega y squared over h bar m omega, that whole thing times the wave function, and set it equal to 0. So now I'm going to multiply an h bar m omega on all terms, and I get the second derivative of the wave function plus 2 times the energy divided by h bar omega minus y squared, I'm sorry, this should be this whole quantity in the denominator squared. Okay, so that previous equation is 1 over this h bar m omega times the second derivative plus the energy term minus h bar m omega y squared. That's the substitution for the p squared, and divided by the square of h bar m omega. So then when we multiply by h bar m omega, those things cancel. Okay, and so if we again define the dimensionless energy as the energy divided by h bar omega, then we get a derivative, we get a Schrodinger equation, which is the second order derivative plus 2 times the dimensionless energy minus y squared times the wave function. And we've seen this before. This is the exact same equation we had when we solved the Schrodinger equation in terms of x instead of momentum. So, therefore, the solution to this is a quantized energy of n plus 1/2, or if you want to write it in terms of the total energy, n plus 1/2 h bar omega. So again, we get the quantized energy the exact same way when we started to solve this with Frobenius's method, or the method of a series solution. And that means that our wave function now is going to be of the exact same form as before. There's a normalization constant divided by 2 to the power n prime. You get that from the normalization of the Hermite polynomials. E to the minus y squared over 2 times the Hermite polynomial as a function of y. So it's the exact same wave function, except for now we still have to work out what the normalization constant a is going to be. So we'll do that in a minute. But before we do that, let's substitute back in that y is equal to the momentum divided by the square root of h bar m omega. So when we do that, we get a wave function as a function of momentum, which is a normalization constant a divided by the square root of 2 to the power n factorial, e to the minus p squared over 2 h bar m omega, times the Hermite polynomial of p over the square root h bar m omega. Okay, so now that we've got everything in terms of momentum, let's solve for the normalization constant A. So we're going to integrate over all momentum space. Psi star psi. And we set that equal to 1. Okay, so if we have put this in, what we get is a squared over 2 to the power n factorial e to the minus p squared over h bar m omega. The Hermite polynomials dp. So we have to integrate over momentum now as opposed to position. So the interesting thing is that we've technically solved this integral before in order to get, we came up with the normalization constant in terms of position. And so what we're going to find is that basically everything in this equation is exactly the same, except for x was replaced by momentum. And the constant that we put in front, if you remember, was for the momentum. This momentum is square root of h bar m omega. For the position one, I believe it was x divided by, it was x multiplied by the square root of h bar, no, I'll get this right. It was the square root of m omega over h bar. And so really the only change is that in the x, the m omega really should become 1 over m omega. So we can take our solution from when we solved it in terms of x and just replace, wherever we see m omega, replace it with a 1 over m omega. So when we do that, we get a wave function that is the normalization constant 1 over pi h bar m omega 2 to the power 2n n factorial squared, all of this to the 1/4 power times the Hermite polynomial in terms of momentum times e to the minus p squared over 2 h bar m omega. So we now have a general solution for the wave function in terms of the momentum, which is very similar in shape to what we had for the one for position x, except for now it's in terms of momentum and the normalization constant is slightly different. Okay, so if we want, but the problem exercise actually asks for the ground state, so we want n equals 0, which means the Hermite polynomial is 1, and so our ground state wave function in terms of momentum is 1 over pi h bar m omega to the 1/4 power times e to the minus p squared over 2 h bar m omega.